16 million years ago, something tore a hole in the American West so violently that it emptied a magma chamber the size of a small sea. 1,000 cubic kilometres of molten rock blasted into the sky. Ash clouds rolled across what is now Nevada and Oregon, and the ground above the magma chamber simply gave way. The land didn't just crack, it collapsed. What remained was a caldera. A giant volcanic depression formed when the roof of a magma chamber caves in after an eruption. Today it looks quiet, wind-scoured, and almost ordinary, but beneath that ancient scar, geologists have just confirmed one of the largest lithium accumulations on Earth, a discovery valued in headlines at around $1.5 trillion. That number alone is enough to rattle geopolitics. Lithium is the backbone of modern batteries. Electric vehicles, grid storage, smartphones, defense technologies all depend on it. Control lithium and you influence the pace of the energy transition. Lose access to it and entire industries slow down. For decades, much of the world's lithium supply has come from South American brines and Australian hard rock mines. Now buried inside the remains of an ancient supervolcano in the United States lies a deposit so large it could reshape supply chains. But here's the real story. The eruption didn't directly create the lithium deposit. It created the conditions, and that difference matters. When that Miocene supereruption detonated, it expelled enormous volumes of rhyolitic magma. Rhyolite is a silica-rich volcanic rock, sticky and gas-charged, the kind that produces explosive eruptions. But this wasn't just any rhyolite, the magma was unusually enriched in lithium. Melt inclusions, tiny pockets of trapped magma preserved inside quartz crystals, show lithium concentrations many times higher than average continental crust. In simple terms, the magma was chemically primed. That was pathway number 1, an unusually lithium-rich magma source. As the eruption emptied the magma chamber, the roof collapsed, forming a caldera roughly 40 kilometres across. If you've ever seen Crater Lake in Oregon, that's a caldera. Now imagine one even larger, but filled not with deep blue water, but with ash, pumice, and steaming volcanic debris. After the eruption, the violence stopped. The ash settled, rain fell, the collapsed basin became a closed depression, meaning water flowed in, but didn't drain out to the sea. Over time, a lake formed inside the caldera. That was pathway number 2, a closed hydrologic system. In plain language, the basin acted like a giant bathtub with no plug hole. Most volcanic systems don't get this combination right. Some erupt lithium-rich magma but remain tectonically active, fractured and leaky. Fluids escape. Lithium disperses. Others form lakes but from magmas that aren't especially enriched. The chemistry just isn't there. At McDermitt, both conditions aligned. Now here's where it gets quietly brilliant. The ash that filled the basin wasn't inert. It was mostly volcanic glass, tiny shards of rapidly cooled magma. Volcanic glass is unstable at Earth's surface. When it reacts with water, it breaks down into clay minerals. This process is called diagenesis. That's just a technical word for chemical alteration of sediments after they're deposited. As the volcanic glass altered, lithium was released into the lake waters. Because the basin was closed, the lithium couldn't flush away to the ocean. It stayed trapped. Evaporation concentrated it further. Over thousands, then hundreds of thousands of years, lithium became incorporated into newly forming clay minerals. This is pathway number 3, long-lived diagenetic trapping inside a closed basin. The lithium didn't crystallize into shiny veins like gold in quartz. It bonded into microscopic clay particles, particularly lithium-rich illite and smectite. These are sheet-structured clay minerals. Think of them like atomic scale stacks of paper, with lithium atoms tucked between the sheets. Over time, these lithium-bearing clay layers accumulated to significant thickness. In some zones, grades approach 0.3% lithium, enormous for a clay-hosted deposit. And because the enrichment was sedimentary, the deposit is laterally continuous, spread out in layers rather than narrow veins. Most Yellowstone hotspot calderas don't preserve this trifecta. They may have lithium-rich magma, they may have hydrothermal systems, but they don't stay closed long enough. Faulting opens pathways, fluids escape, the lithium system leaks before it can mature. McDermitt didn't leak. Instead, it simmered. For over 1 million years after eruption, chemical reactions quietly reorganized the volcanic debris. Lithium moved through pore waters. It attached itself to clay structures. A giant stratified lithium reservoir formed without a single dramatic mineralizing event. No violent hydrothermal breccias, no boiling geysers depositing veins, just water, glass, time and containment. And here's the geopolitical pivot. Modern civilization runs on lithium-ion batteries. These batteries depend on lithium's ability to shuttle between electrodes while remaining lightweight and energy dense. Energy density is just a measure of how much energy you can store in a given mass. Lithium excels at this because it's the lightest metal. Electric vehicles are projected to dominate transportation within decades. Grid storage systems are scaling rapidly to stabilize renewable power. Defense sectors rely on advanced battery systems for everything from drones to communications. Until recently, global lithium supply was concentrated in a handful of regions: the lithium triangle of Chile, Argentina, and Bolivia, and the hard rock spodumene mines of Western Australia. Strategic dependence on foreign lithium has been a concern for major economies. Now imagine a domestic deposit capable of supplying a substantial fraction of future demand. A $1.5 trillion in-ground valuation doesn't mean $1.5 trillion in profit. Extraction costs, environmental constraints, processing complexity, all of these matter. Clay-hosted lithium is more chemically challenging to process than brine or hard rock, but a sheer scale changes leverage. It shifts negotiation power. It strengthens domestic battery supply chains. It reduces vulnerability to global disruptions. All because 16 million years ago, a magma chamber emptied. Let's rewind to the eruption itself. The McDermitt supereruption expelled roughly 1,000 cubic kilometres of magma. To put that into perspective, the 1980 eruption of Mount St. Helens released about 1 cubic kilometre. The McDermitt event was roughly 1,000 times larger. As the magma chamber drained, the overlying rock collapsed along ring faults, fractures forming a roughly circular pattern. These ring faults defined the edges of the caldera. Collapse wasn't instantaneous. Blocks of crust sagged and tilted inward. Intra-caldera tuff, welded volcanic ash, accumulated to thick sequences inside the depression. After collapse, magma continued to intrude beneath the caldera, causing resurgence, uplift of the central region as magma pushed back upward. Resurgence is like the centre of a trampoline bulging upward after being depressed, but eventually magmatic activity ceased. Silence followed violence. Rainwater collected in the basin. Sediments washed in from the rim. Volcanic ash layers altered. Zeolites formed. These are hydrated aluminosilicate minerals that trap water in their structure. Feldspar crystallized during chemical alteration. Clay minerals proliferated. Lithium, released from glass and possibly augmented by residual magmatic fluids, entered the lake water. Evaporation cycles concentrated it. The chemistry shifted over time. Lower sections became dominated by lithium illite, upper sections by lithium smectite, a layered chemical story written in mud. Over millions of years, erosion buried and exhumed parts of the basin. Tectonic extension gently tilted the caldera region eastward. The lithium layers remained largely intact, preserved in a sedimentary fill. Today, drilling at Thacker Pass and surrounding areas confirms vast tonnages of lithium-bearing claystone. Resource estimates reach into the millions of tons of contained lithium metal. From a distance, the site looks unremarkable. Rolling sagebrush, open sky, dusty ridges. It doesn't scream strategic resource. But beneath that quiet surface lies a chemical archive of volcanic catastrophe and hydrologic patience. This is what makes the story so powerful. The supervolcano didn't directly mint a lithium treasure chest in a single explosive act. It set the stage. It supplied enriched magma. It built a closed basin. It left behind reactive glass. Then geology did what geology does best. It waited. Time is often the missing ingredient in ore formation. We tend to imagine deposits forming in dramatic bursts. Hydrothermal explosions, metallic veins shooting through fractures. Some of the world's largest resources form slowly, chemically, almost invisibly. I hope you found this as interesting as I did. And as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.